Well, greetings, mathletes, and welcome back. Today we're going to be talking about solving exponential and logarithmic equations. Now, we've introduced exponential functions and logarithmic functions. We've used the properties of exponents, but we actually covered them in a previous course. But the properties of logarithms have just been introduced. You may or may not have seen those in a previous course, but we're going to have to use all of those things, including the definition of each one of those exponential and logarithms, to be able to solve exponential and logarithmic equations. And so that's where we are now. The next place we're going to go in the next lecture, and so that would actually, I think that's going to be after spring break. But the next lecture, we're going to be covering how to apply all this stuff and actually use it to find things out. So we'll get through all this mechanical stuff, and then we'll start applying it. And that's really kind of the more artistic side of it, is knowing when to use it and how to use it. Okay, so let's go ahead and get started here. So if we're going to solve exponential and logarithmic equations, okay, we rely on a couple of things. Okay, so first of all, the fact that both exponential functions and logarithmic functions are one-to-one functions give us the following properties. So this is our one-to-one property. And it actually, they'll make sense when I write them down. So if I have some base raised to some power, and it's equal to another quantity that has the same base, right? So the bases are the same, but the exponents may or may not be the same. Really, the conclusion that we get from this, if these bases are equal, then the exponents also have to be equal. So if we have this, then we get that x is equal to y, right? We can just set the exponents equal to each other. Likewise, and this is also the one-to-one property for logarithms. If I have like bases in the log, right? So everything's the same except the argument of the log. So if this is the case, then x is equal to y. So one of the goals that we're going to have when we're solving these is see if you can rewrite them so that they have the same base. That way you can set the exponents equal and just solve a regular equation instead of an exponential one. And the same thing with the logs. If we can get one log equal to another log, then we can set the arguments equal to each other and solve that equation, whatever it happens to be. So as we go through this, one of the things you're going to notice is that we have other types of equations to solve in the process of solving exponential and log equations. So all of that stuff that that you covered in your algebra courses and your trig courses, all that stuff, well, maybe not the trig in this section, but all of that is going to apply. You need to know how to solve quadratics. You need to know how to solve rational functions or rational equations. Just all of that stuff, they all pop up. Okay, so this is the one-to-one property. The other property that we're going to use is the inverse property. So there's one-to-one property. I'm just going to go ahead and, well, let's move my face. There we go. Let's look at the inverse property. Okay, this is the other property that we're going to be using. So basically, if b to the x is equal to y, then x is equal to log base b of y, right? So you can actually, this is basically rewriting it in its logarithmic form, right? And if you do that, you can come up with an answer. The other way is if we have log base b of x equal to some number. Well, I used y before. I'll use y again. Equal to some number. Then I can rewrite it as an exponential. B to the y is equal to my x. Right? Now, that's using the definition. One of the ways you want to be thinking about this, too, particularly with the exponential stuff, Let's see, I'm going to need a little bit more room here, I think. Let's see if we can move some stuff around. Yeah, so we'll just look at it with the exponential here. If I have b to the x equals y, what we're actually doing is taking log base b of b to the x of both sides, or log base b, I'm running out of room. Okay, right, so we basically just did this, and then I pulled the exponent out to the front, right, and log base b of b is 1, so x is equal to log base b of y. Right, so it really is just applying the inverse to both sides, and we're going to be doing this both ways. Okay, so those are the two properties we're going to be using. Let's actually just get in here and look at some examples. One of the things I want you to remember as we go through this, and I'm going to step out here and just say this directly, is that particularly with the exponential equations, there's usually two techniques. Right, and both of them, well, sometimes both of them work, sometimes only one of them work. But it's very much like solving quadratics in this sense, that sometimes you can solve it by factoring, and if factoring works, it's the way faster way to do it. But if factoring doesn't work, there is a way that always will work, but sometimes it's a little clunky and a little more technical. You know, you use the quadratic formula or something like that. Factoring is way faster if it works, but it doesn't always work. Right, and that's how it's going to be with these exponentials. The first way we're going to look at this doesn't always work, but if it does, it's way faster. Okay, so we'll start there. So let's step back into the lesson now. Okay, so first let's start with exponential equations, and we will say that we have 2 to the x is equal to 16. Okay, so with 2 to the 16th, it's probably for quite a few of you, you can see what x is, that you can see ahead of time that x has to be 4. First of all, if you can see it, that is a legitimate way to solve it, because it's very easy to demonstrate that 2 to the 4th is 16. However, you're not always going to be able to just see it. So what we want to do here is, the first thing you want to be thinking is, can I rewrite this so that they have the same base? Right? Now, sometimes, and again, you probably don't have to do this with 16, but I'm going to demonstrate the process anyways. If you want to know how you can factor 16 out, you just do a prime factorization, you know, do a factor tree or what have you. Right, and I can see that it's 2 to the 4th. So this is what you do if you're having issues with, you know, what power of whatever is this. You just factor it out and see what powers it is. This is 2 to the 4th. So once we rewrite this as 2 to the 4th, that's our one-to-one property. I have the same base. That means the exponents are equal, which means that x is equal to 4, because x is the first exponent and 4 is the second exponent. Right? And so that's the process. Rewrite them so they're the same base, set the exponents equal. Okay, so let's take a look at a couple more, because these actually do go fast. I know my explanations get a little long-winded sometimes because I'm trying to talk about the nuances and stuff. But so let's actually redo this, and we'll change it so that maybe it's not so obvious. So we'll look at we'll do 16 to the 3x. And then also I want to do 7 to the x is equal to the square root of 7. Okay, so these are the two I want to work on. I would actually suggest that you pause and just see what you can get done on this, because, you know, you may hit a stopping point at some point, and that's fine. But then you'll see, when you watch the solution after that, you'll be watching the solution with a question in your mind, and you want to get a question answered. So you'll actually appreciate the solution a lot more if you try to do it first. Nonetheless, let's go ahead and do this. So we already know that 16 is 2 to the 4th from the last problem. So I'm going to rewrite this so that 16 is 2 to the 4th. Right, so now we have 2 to the 4th raised to the 3x. Well, properties of exponents say that I can go through and multiply these two things. So that means that 2 to the 4x minus 1 is equal to 2 to the 12x. Okay, we've gotten it now to the point where we have like bases again. If we have like bases, we set the exponents equal to each other, which means that we get 4x minus 1 is equal to 12x, because those are our two exponents. Now, this is just a regular linear equation now, right? There's no squares, there's no square roots, there's nothing fancy we have to do. We just need to isolate x, get x on one side, numbers on the other. And since it's going to stay positive if I go this way, I'll do that. So I get -1 is equal to 8x, which means that x is equal to -1/8. I reverse the order of that. But that's our solution here. And you can actually check it just by plugging these things in. Well, I'm going to check it, and I still want room to work on this one. So let's check it. So we have 2 to the 4 times 1/8 minus 1 is equal to 16 to the 3 times 1/8. Oh, -1/8. I forgot my sign. It's so easy to forget signs. Signs are real easy to forget, and so oftentimes people, sign mistakes are kind of forgiven, but sign mistakes can be very, very important. If you don't think signs are important, change the sign on the balance of your bank account and see if that doesn't change anything, right? Signs are important. Okay, so looking through this, all I have to do is simplify these and make sure I get the same answer on both sides. So let's see here. 4 times -1/8 would be -1/2. So that's 2 to the -1/2 minus 1, and that would be 2 to the -3/2. And then we need to simplify this. So this should be, well, actually, I can do that a lot quicker. Let's see if that's equal to 16 to the -3/8. Okay, so what we're going to do here is we are going to pull up our magic calculator and just plug both of them in. Right? We can clear things out this way. So let's see, 2 raised to the -3/2 is that number. And now we just need to do 16 raised to the -3/8. And we get the same number. So that means it works. Right? You could actually take it farther and do a little bit more by hand, but you'll have a bunch of expressions with square roots in it and things like that. They get a little bit messy. Right? So in any case, you just plug it in to see if it works, just like every other equation. If it's a solution to the equation, it makes the statement true. Okay. So we have that. Let's go ahead and look at the second one here. I'm going to go ahead and get this part off. Now, this one might look a little bit different because that square root sometimes throws people off. But remember that square roots are exponents, right? Square root of 7 is the same as 7 to the 1/2 power. And so roots, well, they become pretty quick to take care of. You just make sure you put a fractional exponent and then deal with it the same way we have been. X is equal to 1/2. That's it. Right, so a lot of these go really quick. Some of them take a little bit more work like this, right? But if you can find like bases, you can always solve the equation. Okay, so let's go ahead and delete that, and we'll look at the next couple examples here. Okay, so let's look at 9 to the x is equal to 1 over the 4th root of 3. Okay, and then the other one I want to try is e to the x plus 4 is equal to 1 over e to the 2x. Okay, so those are the two I want to work on. What I want you to do first is try to do these yourself, right? So pause your video, see if you can work them out. You've seen enough of the little details. There's a little bit more, but you have covered this stuff already. So see what you can do with it, and then we'll look at it together. Okay, so let's see. We want to rewrite these so that they're the same base. So first of all, I need to write this right-hand side as an exponential, in some kind of an exponential fashion. I know a fourth root is a 1/4 power, but it's in the denominator, which makes it negative 1/4. So the right-hand side is 3 to the negative 1/4 power. Okay? Now, this is not a base of 3, that's a base of 9, which is a bit of an issue. So what we can do here is 9 is 3 squared. So I'm going to write 3 squared raised to the x. Well, that means that this is 3 to the 2x, and the right-hand side would be 3 to the negative 1/4 x, and now we can use the one-to-one property, right? 2x is equal to negative 1/4 x, or negative 1/4, sorry, there's no x on the right. Right now, all we have to do is just divide by 2. So if I divide both sides by 2, I get x is equal to negative 1/8. Oh, we got the same answer again. What do you know? That's a coincidence. But nonetheless, this is still our answer, right? So it's setting the bases equal to each other. Once you have the bases the same, once you find like bases, you set the exponents equal and solve whatever equation falls out of it. Okay, so that's this one. Now, if we look over here, we've changed the base, right? We have a base e now instead of a base whatever, right? So we have e as a base. That doesn't change anything, right? We still want to just make sure we have the same base on both sides, and we set the exponents equal to each other. So the left-hand side already has a base of e. The right-hand side, I can rewrite this as e to the negative 2x, right? Bring it to the top and change the sign of the exponent, which means that x plus 4 is equal to negative 2x. So let's see here. If I go ahead and subtract this over, I get 4 is equal to negative 3x. And if I divide by negative 3, I get x is equal to negative 3/4. Right? And so it just comes back down to solving whatever equation falls out of it once you get like bases. Okay. Now let's go ahead and take a look at the next one here. And let's say that, and I'm going to let you work on this first, 3 to the x is equal to 5. Okay, so go ahead and pause this and see if you can find like basis for this and come up with a solution for x. Okay, I'm assuming you've paused now. And my guess would be you couldn't find like bases. There are like bases, but they're irrational numbers, right? So 3 is not an easy power, or excuse me, 5 is not an easy power of 3. So we have to do this another way. This is where we use the properties of logarithms, right? One of the things we can do, all you have to do is just pick a log that's on your calculator, either the common log or the natural log. Most people use the natural log, but if you have like a bunch of 10s, 1000s, 100s, powers of 10 in your problem, it's a lot easier if you use a common log. So I'm going to use the natural log for this. So I'm going to take the natural log of 3x on the left-hand side and the natural log of 5 on the right-hand side. So I'm doing the same thing to both sides of an equation. Now we're going to use the properties of exponents, or excuse me, properties of logs, right, and bring that x down to the front. So now we have x times the natural log of 3 is equal to the natural log of 5. Well, the natural log of 3 is just a number. So this is a number times x equal to another number. So all we have to do is divide by the number that's multiplying by x, which in this case is the natural log of 3. So that cancels out, and I end up with x is equal to the natural log of 5 divided by the natural log of 3. Now, here's the deal with these. This is an exact answer. This is absolutely a perfectly exact answer. So anyone who has this value, they can plug it into a calculator, and they can get a decimal approximation as far out as they want, right? Whatever they happen to need for their purposes. However, a lot of the time you just need a decimal approximation. And so, again, we are going to basically just plug this into the calculator to get a decimal approximation. So we're going to, in fact, let's take it to 3 decimal places. I think your homework kind of wavers between 2 decimal places and 3 decimal places, depending on what you're looking at. But nonetheless, let's move this over here. Let's do the natural log of 5 divided by the natural log of 3. And we'll just hit enter. And so this is approximately, we said we're taking 3 decimal places, so this is 1.4, I lost it. 465. Yeah, there we go. 465. Right, and so there's our decimal approximation. So we have 2 answers. The one that has all the logarithms in it is exact. This one is an estimate. Right, so be aware of that. Any decimal approximation is an estimate, not an exact answer. Okay, so that's the procedure when we cannot find like bases. If you can find like bases, it works pretty quick. You may think that it works pretty quick this way and you want to just do all of them this way, and that's fine. You'll still get the correct answers. But oftentimes, when you can see the like bases, sometimes you can just look at it and see the answer. So it's a little quicker that way. All right, so let's take this a little bit further. Let's say we have 10 to the x is equal to 3.62. Now, this is one of those ones where, again, you can definitely take the log of both sides, no problem. But you notice this number has a base of 10, right? 10 to the x is an exponential base 10. If you use the log base 10, you get an answer a lot quicker. So if I take log base 10 of both sides, log base 10, right? Well, log base 10 of 10 to the x, because this is a base 10, even though we don't write it. So that means that the left-hand side is just x. So x is equal to the log of 3.62. I don't even have to do any adjustments. I can plug it directly into my magic calculator box. Again, the log of 3.62 is the exact answer, right? So we're going to use log, and it's that's not a point. Let's try that again. 3.62, and we close her up. Boom. So we want an estimate. X is approximately, I lost it again. 0.559. Right, if we round to 3 decimal places. If we round to 2, it'd be 0.56. Okay, so that's using logs on both sides of an equation to solve the equation. And we're going to take this and go a little bit farther with it. So let's see what else we got here. All right. So these will be 2 for you guys to solve, and then we'll get to some of the fun ones. So let's do e to the 1 minus 5x. No, I don't want to go that far yet. Yeah, we'll do e to the x equals 5. And then the next one we'll do is, let's put that other one in there now. We'll go ahead and do this anyways. Okay, so there's 2 to play around with, and see what you can do. Okay, I'm assuming you've played around with it. Now, the fact that this is an exponential in e, with a base of e, tells me that the way I'm going to solve this is by using the natural log, right? Once you get fast at these, you can actually just look at them and you know some of these answers. Like this one, I know automatically this is the natural log of 5, right? And that's because if I take a log base e, right, it would be e to what power is 5. I'd write it that way. Well, log base e is the natural log of 5. Right? So whenever you have an exponential in e, use the natural log. And then the natural log of 5, where'd it go? There it is. Oh, it's always on top of my work. Right? We can just plug that into the calculator. So it's approximately 1.609. Right? And that's just from the calculator. Be glad you don't live at a time when you had to do these by hand. It was much more painful. Okay, now looking at this one's a little different because I have extra stuff up here, right? But it doesn't change anything. If I take the natural log of both sides, right, what I end up with, well, natural log is base e, so these bases cancel out and I just get the exponent. Okay, now the natural log of 793 is a number, right? It's an exact number. It's an irrational number. It goes on forever. I'm going to leave it as the natural log of 793 until I'm done, so I can see the full exact answer, and then I can find a decimal approximation. So the goal is still to get x by itself. This is just a number, so we'll do exactly what we have always done before. We'll subtract 1 from both sides. That will give me negative 5x is equal to negative 1 plus the natural log of 793. Right? We don't have an exact number for it, so we just leave it there like that. It's kind of like a square root. Right? 1 plus the square root of 3, you can't combine them because they're not really like terms. Then we'll divide by negative 5. Right? So that's there. I get x. And I don't like these negatives here. So I'm going to multiply top and bottom by negative 1 to change all the signs. So this is 1 minus the natural log of 793 divided by 5. Right? And so all of the signs changed because I multiplied top and bottom by a negative. So we have that. Now we need to be able to plug this into a calculator for an estimate. So I'll put the estimate on the other side here. So pull that back up, come over here, and we need, if we're going to plug this in all at once, 1 minus the natural log of 793, close that. Now, I also need to close the numerator. I put open parentheses to open the numerator, and then I'm going to divide. So the entire numerator is in parentheses, and I want to divide that by 5, and we'll see what we get. Oh, there we go. So this is approximately negative. Oh, I'm going to look at the answer before where to go. There it is. Negative 1.135. So it's negative 1.135 if we take it to 3 decimal places. It'd be negative 1.14 if we took it to 2. Okay. So we have that. Now, sometimes these things are housed in weird little things. So let's look at one more here just so you have an idea of what's going on. So let's suppose we're handed this instead. E to the 2x minus 3 times e to the x plus 2 is equal to 0. Okay, so the first problem right off the bat is like there's not an exponent, there's not quantities on each side that we can turn into exponentials, right? So that's the first problem. What's difficult to recognize here is this is actually a quadratic equation. Okay, so you have to be able to recognize these things. If I take e to the x and square it, this is e to the 2x. So e to the 2x is a squared term. E to the x is not squared, and then I don't have that term at all in the last, I don't have that variable at all in the last term. So what we're going to do is we're going to turn this into something that looks more quadratic-ish. I'm not sure if that's a word, but we'll go with it, quadratic-ish. So I'm going to make a substitution. I'm going to say u is equal to e to the x, because that's what I was squaring here. So that means that u squared is equal to e to the 2x. So that means right here where I have an e to the x, I can put a u since they're equal. Same thing here, e to the 2x, I can put u squared. So this is now u squared minus 3u plus 2 is equal to 0. So this actually factors. This ends up being, not x, u. U minus 2 times u minus 1 equals 0. And jumping through the steps here, I end up with u equals 2, and I end up with u equals 1. Okay, well, we're not solving for u, we're solving for x. So what we do is we make our substitution back with this. U is e to the x. So that means that e to the x equals 2, or e to the x is equal to 1. Right? Okay, well, if e to the x is equal to 2, I can just rewrite this as a natural log. This would be the natural log of 2 is equal to x. That's one solution. Over here, what power of e will give me 1? Well, there's only one. It's 0. X equals 0. Right? And so I have two solutions here because the original equation was quadratic. Right? So this is actually our trick. Most of the time when you see e to the x, you want to look to make sure that e to the x is being squared somewhere. If you have an, and I want to point this out too, if you have something, well, let me switch colors so it doesn't look like I'm working on the same problem. If I have something like e to the 4x, well, this is the square of e to the 2x, right? Anytime you have an even exponent, you can always write it as a square, right? You can always pull that 2 out as a separate exponent. And so if you have this term as your biggest term, u will be e to the 2x. If you have this term as your biggest term, then u will be e to the 3x. So it's just whatever half of that is. And then you go and make your substitution, solve your quadratic, and then substitute back to e to the x so that you can solve your final exponential function. So these get kind of involved, right? You have to pull from a lot of different areas of mathematics as you're going through it. But as long as you make sure you don't panic and take your time and think about what you might need to do, you should be able to get through these. All right, so let's go ahead and clear that off. And now we look at log equations. And so we'll just start building these up as well. So if I start with a log equation, when it's something like log base 3 of x is equal to 4. One of the easiest ways, and one of the most straightforward ways anyways, is to just rewrite it as an exponential, right? Which means that 3 to the 4th is equal to x. So all you have to do is compute 3 to the 4th. And that's 81. So 81 is equal to x. Log base 3 of 81 is equal to 4. Right? Pretty straightforward, right? It's just a matter of deducing what needs to be in there. So if we up this a little bit and look at something like, let's do log base 3 of 3x plus 2 is equal to 4, right? You notice we have pretty much the same setup here. It's just instead of just an x in here, I have an expression. It doesn't change anything. It's still the base to the answer is the argument. So 3 to the 4th is equal to the argument, 3x plus 2. And so that means 81. That's not an 81. Let's try it again. 81 is equal to 3x plus 2. Well, that's a linear equation, right? Same old thing we've always been solving since the beginning of algebra. So if we go ahead and add 2, that gives me 83. Add 2. Subtract 2. That gives me 79 is equal to 3x. And if we divide by 3, we get 79 thirds. Now, 79 thirds is a fraction, it doesn't reduce, right? You could switch it to a mixed number or something, but there's nothing wrong with leaving a fraction this way. There's nothing actually improper about an improper fraction. It's an unfortunate name, actually. These are numbers just like everybody else, so we can treat them the same. Okay, so those are the basic ones. Then there's the ones that actually require you to use some of the log properties. So let's take a look at some of those. So let's say I have log base 6 of x plus 5 plus log base 6 of x is equal to 2. Okay, so this is kind of interesting. So let's see what we got here. Let's see. Oh, we have an addition of 2 logs. Oh, that makes it look like it's a plus or minus. So what that means is that we can combine the arguments using what we did in the last section, right? This is a sum, it turns into a product. So I can change this to log base 6 of x times x plus 5. And that's equal to 2. Well, you notice this is the same, now it's in the same form as the last type of problem, right? So all we have to do is rewrite it as an exponential and solve the resulting equation. So 6 squared is equal to this argument, right? Well, we can't solve it in the form it's in, but if we square this, 36, and we distribute this, I can see that this is actually a quadratic equation. So if I subtract the 36 over, I end up with x squared plus 5x minus 36 is equal to 0. This left-hand side actually factors. Okay, now, let's see here. That's going to be x and 36, so it's going to be plus 9 minus 4, right? Which means that x is equal to negative 9 or x is equal to 4, right? Those are our two choices. We have to be very careful with these log equations because when you take a log, right, x has to be at least 0, right? Whatever the argument of a log is, it has to be a non-negative number. So we need to check both of these. The one that seems like it's going to cause problems might be this one, but we do need to check both of them. Because if it turns out I'm taking the log of if the number inside of a logarithm is negative, I'm not going to get an answer. And actually, before I continue with that, this is a little aside. There is actually an answer. It just turns out it's a complex number, and so we're not heading down that direction right now. You don't get real solutions by plugging negatives into logs, but you can get complex solutions. So it's kind of interesting when you look at it. Once we get to that point, hopefully we'll have time to cover that this semester. Okay. In any case, we're not going to be able to take the log of a negative number, and I can see negative 9 actually causes problems with both terms in the original problem. And you have to check it in the original problem because once you get here, negatives disappear, right? You have to check it with the original problem. If I do negative 9 plus 5, I get the log base 6 of negative 4, and that's a problem, right? We're not going to be able to do that right now. So that means negative 9 can't be, and it actually doesn't work in this one either, but you only have to find one place it fails for it to fail completely. And then I can see with the 4, with x equals 4, that I won't get a negative answer or negative argument for either one of these, which means that my solution is x equals 4. So when you get more than one solution, you have to check them, especially with logarithms. Not so much with exponentials, but with logarithms, definitely, because not all answers that you get from following the solution steps will work. Okay, so let's take a look at another one. And remember, when you're doing these, it's just a matter of trying to get it down to one log, right? If you can get one log on both sides or one log on one side, that's usually where you're headed. Okay, so let's look at this. Let's say we have log base 4 of x plus 2 minus log base 4 of x minus 1 equals 1. Okay, so let's go ahead and play with this here. Now I have a subtraction here, because remember my goal is to get everything down to one log on each side, unless there's no logs on one side. But this is a subtraction, which means this is the same as log base 4 of x plus 2 over x minus 1. And that's equal to 1. Okay, so if we want to solve this, that means 4 to the first power is equal to x plus 2 over x minus 1. Right? Okay, well, if I want to solve this, I'm going to cross multiply. So that means 4 times x minus 1 is equal to x plus 2. Right? So 4x minus 4 is x plus 2. If I go ahead and add 4 here and subtract x here, I end up with 3x is equal to 6, and so x equals 2. Now you still, even though that's a positive number, you still want to check because you have a subtraction in one of your arguments. That subtraction could end up making this negative. So let's just double check. So I have x is 2, so that means my two terms are log base 4 of 4 plus 2, so that's no problem. That's a green check mark. And log base 4 of 4 plus 2. It should be 2 plus 2. I was thinking the answer. Right, because x is 2. So we're just plugging the 2 in there. And then we're going to plug the 2 in here and make sure we're okay. 2 minus 1, well, that's the log base 4 of 1. So that one's also a green check mark. Right, I don't have a negative number inside the log, which means that this is my answer. It works. But you notice we had to use the properties of logarithms to be able to play around with this stuff. Okay, so let's go ahead and take a look at another one here. Okay, and I wanted to expose you to what it looks like when you have logs on both sides of these things as well, on both sides of the equation. So let's say we have log of 3x minus 3, and that's equal to the log of 2x plus 3 plus the log of 2. Okay, remember the log of 2 is just a number. Okay, so there's more than one way to get a hold of these things, but I think probably the nicest way to go, since I have logs on both sides now, is to combine all the logs together on whatever sides I can. So I'm going to combine these two guys into log of 2x plus 3 over 2. Oh, not over 2, times 2. I'll just do it this way. 2 times 2x plus 3. Right? Okay, well, note, first of all, that we have a common log on both sides here, but they are the same log. And so I have two logs equal to each other, which means that this argument has to be equal to this argument. So I'm going to do that. 3x minus 3 is equal to, and I'm going to go ahead and distribute at the same time, 4x plus 12. And so we just need to solve this now. Right? So I'll add 3 and subtract 4x from both sides. And that gives me negative x is equal to 15. And, well, let's see here. Did I do something wrong? Because this looks like it may have no solutions. This is interesting. If negative x is equal to 15, then x is equal to negative 15. Well, this raised my attention. I'm not seeing anywhere that it wouldn't be. Okay, so let's now check to make sure they don't cause any problems in our logarithms. So if I have log of 3 times 15, 3 times negative 15 minus 3. That is the log. Let's see, 3 times 15 is 45. So it's negative 45 minus 3. That's the log of negative 48. Now, even if it works in the other log, this is enough where we have to go, that answer doesn't work, right? All it has to do is fail in one place, and it's no longer an answer. So this one isn't an answer, even though it looks like an answer. This is an extraneous solution, meaning that we followed all the steps correctly, but the solution we got doesn't work. Okay, so it's extraneous, it's extra. Not all of these end up like this. Sometimes they work, sometimes they don't. What I wanted to emphasize to you guys is that when you have logs on both sides, you just want to condense each side down to one log and then set whatever's left equal to each other, right? Whatever's inside the logarithm, these things get set equal, right? Same way that you set the exponents equal when it comes out that way. So the reason we learned all those properties was to be able to navigate equations. The reason we're learning how to navigate equations is so that we can apply them to find things out. And so we're going to see a few examples. We might actually spend the whole first week after the test just going through examples of how exponential and logarithmic functions are used, and how to deduce things. In fact, I already have a discussion board planned for us that where we actually have to make a prediction based on some information that we're given. So in any case, that's what we got for today. And so until next time, keep your pencils and your wits sharp.